We're now going to move on to the reasons why we have been studying complex numbers over the last few lectures. And this is not because there's some nice mathematical abstraction. The reason we have been looking at complex numbers is because of their importance in a wide range of areas of computer science. So the first one I'm going to look at is a topic which are called quaternions. And quaternions are very important in realizing quite sophisticated three-dimensional graphics effects where we encounter problems if we try and realize those effects by using matrix and vector products. So, what are quaternions? Well, the first thing I should say is there are not so much an application of complex numbers in themselves. They are a mechanism that arises, that came about by trying to extend some of the geometric aspects of the complex plane and two-dimensional vectors. In particular, quaternions arise through trying to answer the question, how do we develop this formalism called the complex plane, which is in two dimensions, to a three-dimensional setting? And the answer may seem a little bit surprising. The way we do that is by looking at a vector formalism, a vector algebra, not with three components, but with four components. And as I said, the solution the quaternions provide, this gives us a very effective set of computational methods which we can use in implementing three-dimensional computer graphics effects. So we saw this form for complex numbers as using two real numbers. So we had one real number added to this object I multiplied by another real number. And the form, the real part and the imaginary part, is to find a vector or a point in the complex plane. The other innovation we had was this object I had the property that when we squared it, the outcome was -1. But in effect, what we are dealing with are two real numbers, pairs of real numbers. For quaternions, instead of two vectors, we are using four vectors. So quaternions we can think of as points in four-dimensional real space. And the way we write a quaternion is just as a quadruple of four real numbers. And corresponding to our standard form for complex numbers, as this addition of a pair of real numbers, what we now have are the following conventions. We can think of our quaternion as a result of adding our first real number and then I multiplied by x, some new object j multiplied by y, some new object k multiplied by z. So what properties do these new objects have? Well, previously with complex numbers, we introduced I as an item which when we squared it gave us the outcome -1. And these new objects in our quaternion definition, they have the same property. When we square I, when we square j, when we square k, we get the same result, -1. But we now have a new set of objects to consider. What happens when we multiply this object I by this object j, or this object j by this object k. Then what happens is this. We have these perhaps rather complicated set of 6 rules defining what happens when we multiply any distinct pair from these 3 new objects that we've introduced. Before I go on, I'm going to give some of the notational conventions that are used. So, we use this capital H to denote the set of every single quaternion. We're going to use Q to describe an arbitrary quaternion, so an arbitrary collection of 4 real numbers that we want to treat as a quaternion. These forms is general addition form given by adding W for the first of the real parts to I times X, J times Y, K times Z. And we're also going to use a form which is very convenient of regarding a quaternion as some real constant and some 3 vector in real space. So both of those forms are used. In the second of those, as I said, this is a kind of vector convention. The first component is a real number. The second component is a 3-dimensional vector. This notation, comes from Irish mathematician called William Hamilton, who is the person who is usually credited with the development and discovery of quaternions in the mid-19th century. There was some earlier development of very similar ideas, though. Okay, so what are the kind of operations we're going to be performing on quaternions? Well, we have the usual approaches that we've seen already with complex numbers and with vector algebra, and indeed with polynomials. We might want to carry out addition of 2 quaternions. How do we do that? Very much as before, we just add the corresponding components. If we want to multiply a quaternion by some real constant value, again, all we do is we take the 4 individual components and we multiply those components separately by the real constant that we're using. As with complex numbers, we have a notion of the conjugate of a quaternion. And this is in a very similar style to the notion of complex conjugate. What we do, we take the real object, the real constant W, and we don't change that. The 3 vector component, we negate that, or we negate the individual components which involve these 3 new objects that we introduced. We have a notion of size, and once again, this is very much the traditional notion of vector size that we saw earlier. So we take the individual components of the quaternion, we square each of them, we add them, and we take the positive square root of the result. Now this definition, this structure here, it's fairly easy to see. That's exactly the same if we're using this convention of real constant and 3 vector as what the outcome of squaring the real constant, adding the vector size squared to that and taking the square root of the whole computation. So these forms are identical. We have a very special class of quaternions. Just as we had the notion of a unit vector when we looked at vector algebra a few lectures ago, so too we have a notion of something called a unit quaternion. And these are the quaternions which, when we compute their size, the outcome is 1. We have a notion of division, and again, This is very similar to our notion of what we mean when we divide a complex number. So 1 over a complex number was defined to be the object, the complex conjugate, divided by the size of that number squared. For a quaternion, 1 divided by a quaternion is the conjugate of the quaternion, this computation here, divided by the size of that quaternion squared, this object here. Now, where we start running into some difficulties, where we start running into complications, is in defining the notion of what does it mean to multiply one quaternion by another quaternion. So the question, suppose we're given two arbitrary quaternions. How do we form the result of multiplying these two together? How is the product of two quaternions defined? Well, we could start off by taking this summation form for a quaternion and expanding what happens when we multiply this term out by this term. So this is quite similar to what we did with the complex number case, where we only had two components contained within our brackets. The problem we find with doing that, expanding this multiplied by this, is it's extremely messy. And what is happening geometrically when we do that? Well, we saw with complex numbers, we needed the Euler form to make sense of what happens geometrically with multiplying two complex numbers. And it's even more difficult if we're looking at quaternions. So to start off with, we're going to use this real constant in the real 3 vector convention to describe quaternions. And if we use that, what we find is the result of multiplying two quaternions is given by this object here. This looks pretty horrible. Let me just run through what's happening here. So we take the two real constants and we just multiply those. We subtract from the result the scalar product of this 3 vector with this 3 vector. So the dot product that we have here. For the vector component, what we have is we take one of the 3 vectors and we compute the result of the scalar multiple by the real component of the other. We add on to that the outcome of taking the other 3 vector and multiplying that by the scalar component of the other quaternion. So we have these two components here. And for the final contribution, we take the 3 vector cross product of this vector with this vector. So this operation here. So we have an operation that produces a real constant, this one, and a combination of additions of operations which produce a 3 vector. I didn't talk a great deal about 3 vector cross product. We don't really need to know the entire details of its implementation. If you're interested, that can be found in the textbook itself. There's one consequence of this formal definition of quaternion product, and that is the product of quaternions. This is not a commutative operation in general. So the result of multiplying a quaternion S by a quaternion T, in general, that will be different from the result of multiplying the quaternion T by the quaternion S. So this is similar. We've seen this sort of behavior previously when we were looking at matrix product. So how are quaternions helping us with three-dimensional graphics? They seem to introduce a lot of very complicated, sophisticated algebraic formalism. How exactly are they going to help us? Well, first of all, as I said, we looked earlier, we know how to realize graphical effects. We can do them using matrix vector products. So what's the problem with using matrix vector products in 3 dimensions? 2 dimensions, this approach works reasonably well. The problem in 3 dimensions is that one of the things we very often want to do is simulate rotation being carried out. And if we look at the matrices involved, when we're doing this by matrix vector product, this becomes very awkward. It becomes computationally quite expensive. And there's another problem. There is this phenomenon that arises called gimbal lock. So what's gimbal lock? We look at the matrices that are used when we try and do operations in 3 dimensions as a vector matrix product. Then these have to be defined in terms of trigonometric functions, things such as sine, things such as cosine. And what can happen when we combine rotations using certain matrices is the resulting trigonometric functions do not have a defined value. So we can have computations which effectively involve taking the tangent of 90 degrees. And what happens then is that the graphical simulation we are carrying out becomes frozen. It breaks down. So gimbal lock is a problem when we use matrix vectors to implement 3-dimensional graphics. And the case where a graphical simulation is stopping and starting because without knowing it, we've asked for an effect that creates a matrix which exhibits this gimbal lock phenomenon. This isn't a very nice thing. With quaternions, we have a solution. If we use quaternion operations to implement 3-dimensional graphics, we cannot have gimbal lock. So, how do we rotate something about an axis using quaternions? Well, suppose the basic operation we're trying to carry out, we are rotating a point in 3 space about some axis of rotation, some infinite line in 3 dimensions. And let's suppose that line is described by this 3 vector. We're wanting to rotate our point through some angle about this line. And the way we do that is, first of all, we define this quaternion. The cosine of our angle divided by 2 as a real constant, the sine of our angle divided by 2 multiplied by our line vector as our 3 vector. And what happens? First of all, since we're dealing with a line, we can always choose this vector so that the outcome of the length of this quaternion is a unit quaternion. We can always do that. And in order to carry out the computation, rotate this point about this angle, we rotate this point by this angle about this line. Well, all that is this quaternion product. So it's much simpler. We have no trigonometric apart from these cases. We don't have trigonometric operations arising. We cannot have gimbal lock arising because we do not have any stage of that operation which involves computing the tangent function. So let me just summarize what's going on here. Although we don't directly use complex numbers in quaternion algebra, there is a good case for claiming we wouldn't have discovered quaternion algebra without the precedent that complex algebra established. Rotation in 3 dimensions, that's only one of the applications. In many standard popular video games, things such as Tomb Raider, quaternion graphics engines play a large part. Another usage of quaternions, well, there's a module that is taught in year 2, Principles of Computer Game Design, so you'll see more applications of quaternions in that. Other ideas from complex numbers, some of which we'll meet later in the module, these use ideas, these can be extended to quaternions. So one of these is this structure called fractal art. So, I should also say that we can extend things much further. I'm not going to. So just as complex numbers are 2-dimensional objects, quaternions are 4-dimensional objects, there is an 8-dimensional object called an Newtonian, which is a very important in advanced physics. I'm not going to talk about those.